So in today's video, I'll try to explain the new setup or design that I have for my drone, which is called diptera, of course. I basically have, if you can see here, I have a tower of two SPCs and one Pixhawk, which is, I call them three brains. So the drone has basically three brains. Why do I have three brains on board? So this is the first question you will ask. Basically, to include or to increase, the processing power that will basically enable us to perform more tasks, more sophisticated algorithms, and run more nodes on the drone. Luckily, these SPCs do not require a lot of power, and they're not very power hungry. Comparing to computers or bigger motherboards. So why do I have all three on my drone? So all right, let me first explain the hardware on my drone, and then I'll explain the nodes that I have, and then I'll try to show you a small example, a small run test, you can say. All right. So the first thing I want to say is that you already know that we have three SPCs, and I have a depth camera right here, and also have a second camera, which is basically main objective is to run visual odometry or visual slam. The depth camera is main objective is to detect obstacles and try to send commands according to those obstacles, which I'll explain in the notes. All right, so this is my computer here. I want to show you, I'm going to try to explain what I have here. The first part, this part of my screen is basically the terminal of the first brain, and this is the second part is for the second brain. The first part, or the first brain, basically runs the visual odometry or visual slam algorithms and nodes. All right, but however, the second one, also the first one is connected to directly to the Pixhawk. So the first brain has three objectives. The first one is having the localization camera, which runs visual slam. Also is connected to the Pixhawk directly, and the third objective is for it to be a ROS core, the master. So this first brain is the master. The second brain would be running the depth camera and running the nodes that I created for obstacle detection and avoidance. All right. In details, really fast. In details, I have 7 nodes running on the drone. Okay, 7 nodes. The first node would be the Pixhawk node. The second node would be the driver for the visual slam camera. The third node would be the transforms done in order to and the translated visual information that are translated for the Pixhawk to understand. So basically, the third node will be to fuse the information in a Pixhawk. All right. Other services that are not important to explain here. The second computer runs also 4 nodes. The first node would be, this is the driver, which runs basically and starts up the depth camera. I have another node running in the same launch file here, which basically translates the point cloud into a vertical line of points. Okay, to simplify the code and to simplify the movements of the drone, and also algorithms running inside. However, I have 3 nodes here, which I made myself. The first node, which I call diptera obstacle, basically tries to detect the environment wherever the camera is pointing and sees if there's an obstacle or not. how it does that, basically it reads all the point cloud line in that vertical line. It reads all of these points, which are basically the distance from an obstacle to the drone, and takes the minimum point or minimum distance of that scan. All right, and it does that really fast. So if I move the drone, it will basically publish a message saying, if there's nothing, it will say area clear, or if there's something, it will just basically send area blocked. So and here are the just distance between. This is the minimum value or minimum point distance. However, the second node that I have, which is basically the fifth in total, would be the node that will basically listen to the published messages from this node. All right, if it's an area clear, that means it will initiate a movement. All right, it will initiate a movement in a forward direction. Okay, if basically there's an obstacle, if it says, if this node sends that there's an obstacle, this node will basically turn the drone. Okay, so this node basically translates the information here and sends the command, all right, to the Pixhawk directly. Well, I can't say directly because we have the first brain as a master. Therefore, it will go to the first brain, and then through the first brain, it will pass through the Pixhawk and translate those information to movements. What else do I have? I think let me show you a test, a really fast test, just to show you that the drone motors will move. And then I'll explain further information, okay? So, yeah, let me do that, and then I will. Let's take that. Okay, so I'm sure everybody's like, I'm sure that you're asking, why did I touch the remote control? This part is really important as well. However, in order to arm the drone, the Pixhawk basically listens all the time if I'm receiving a radio signal. I keep this for safety. If basically this is shut off, I would not be able to run or fly the drone. The reason for this is, like I said, for safety issues, for safety reasons. Why do I need a remote control? I use this radio. Basically, I programmed all the channels. These are the channels. I pre-programmed all these channels to send commands to the drone, to the Pixhawk directly. So these are quite simple and sophisticated in the same time. Each channel sends a different mode, autonomous mode, to the Pixhawk, which of course would require the information it receives from the SBCs, right, in order to initiate these automatic modes. For example, when I press this channel, it will land, and if you press this channel, it will disarm the drone. So in any case of issues while flying the drone, I can control it with my radio, sending commands to it. The other thing that I will show you here, basically these are commands sent continuously to the, like I said, to the Pixhawk directly. Yeah, this I need to show you a photo to try to explain this. Okay, I have it prepared. So, for example, this is the front direction of the drone. If the drone sees an obstacle in front, what will it do? In my code, it will basically choose a random angle from 4 angles, either 0, 270, 180, or 90 degrees. Okay, then it will move. However, the x-axis will also move if the drone So the nature of my code basically is for my drone is if there is no obstacle in front, move forward, all right, 1 meter. Check again if there's an obstacle. Basically, just turn in your direction in choosing a random angle in these four quadratures. However, if it moves, it should move in a forward direction. However, this forward direction changes depending on the rotation or the heading of the drone. Therefore, my code in that node, basically I try to extract the information of the heading or the rotation of the drone here from the PixHawk. All right, so this node basically reads information from the visual odometry, which basically are fused in the PixHawk, sees where the heading of the drone is, and applies that, includes a 1 meter to that. For example, now we are in plus x direction. The old x value is 0.0018 and the new one is 1.008. This is how my drone basically works. The final thing that I need to explain is just the power source. I power the motors and the main SBC with this this powerful battery, and I also power the new or the third SBC using this small battery. Basically, it's if you can see, it's 28 watt hour. It has 22 volts, and using this DC to DC converter, this is a really powerful high current discharge. It has a high current discharge rate with 4 amps, which is was sufficient for the second PixHawk. We would not use all of it, so I basically tested everything. You saw that everything works, and I'm just waiting. I'm gonna put everything back in and try to test it in the field and let you know what happens. However, the only drawback with this setup is basically adding the weight of this battery and the weight of the third SBC, nothing more. I don't think that's a major that will affect on a flight time. However, I need to test that empirically. The final idea or the major idea of having this setup is basically proving one of the idea proposal that I had is having an SBC or an additional SBC running, communicating as if it's a part of the skeleton or the of that robot, is basically like having another robot, right? So because an SBC is another robot, you just add some propellers and motors to the SBC and you have another drone. What I'm trying to say before trying to say that, the communication here is all wireless. Okay, these SBCs are only connected to their power source and also connected also to the sensors with wires, but they communicate using ROS wirelessly, which means that we can have the drone take advantage of these SBCs on board of other robots to perform higher tasks, or like image processing, deep learning, and these kind of sophisticated algorithms that can that basically lacks in all drones, because they cannot carry or support these carry these SBCs because of the weight, the payload, and also the limited flight time with power source. I hope you got the idea. Please let me know what you think, and thank you for watching.